this webinar on modern enterprise Java architectures with Spring 3.1. We chose that title to focus on the point that Spring really lives within a larger context of deployment platforms, of other frameworks and libraries. And in this presentation, I will actually start with an introduction of that context. Where are things going? What are the trends in 2012? Where is the state of the art in terms of deployment platforms? And from then, we'll take it basically onto Spring 3.1 in a selected feature review. So I will highlight the most important themes and features in the 3.1 release in the second part of the presentation. My name is Jürgen Höller. I'm the Spring Framework project lead. Have been serving in that role for close to 9 years, and it's my pleasure today to talk about the very latest generation of the Spring Framework project. This presentation will primarily focus on Spring Framework, as in the Spring Framework open source project, sometimes referred to as the Spring Core. I will also provide pointers to other Spring open source projects, to sister projects around Spring Framework in several cases. Let's start with an important but basic consideration. In a Spring Framework world, from the perspective of a Spring-based application, we're really talking about an application living in a deployment unit and Spring as a framework living in that same deployment unit, very close to the application. Spring really means it when we say application framework. It's a framework that is very close to your application, supports your application's demands, your application's internal structure. The deployment perspective usually means that the application plus a selected version of Spring of your choice plus third-party frameworks and libraries are bundled up, for example, into a WAR file, a Servlet-compliant web application archive, with all of the frameworks and libraries living in WebInflip, and then being deployed onto a target platform, typically a Servlet container in case of a web application. And what we're seeing here is basically the three key target platforms that we are considering today. Tomcat is a very important, very common choice of deployment platform. Java EE service with WebSphere as a representative, and actually a very important deployment platform for Spring-based applications these days as well. And there's actually a third one coming into the picture here, and that's cloud platforms, so-called platforms as a service, where deployment-wise, we're really talking about the same kind of arrangements, application plus selection of frameworks and libraries, Spring among them, usually the framework of choice to integrate them. This then being deployed onto a cloud platform as a WAR file, since most platforms as a service are designed to accept Servlet-compliant WAR files. So let's focus on cloud platforms for a minute, since this really is an important influence in terms of what how Spring is positioned today, and in terms of the priorities in some of the feature areas that we invest into. So cloud platforms are actually known as platforms as a service, or PaaS. What we mean here is a layer above the typical infrastructure as a service arrangement, where we really get a full, rich application-level deployment platform. Basically, we're talking about hosted services in case of a public cloud, a service hosted in the internet that accepts WAR files. Let's focus on that for the moment. Servlet-compliant WAR files, and runs your application within the cloud platform, within the cloud service provided by that specific provider of choice. In case of a private cloud, you're actually running such an infrastructure yourself. So in case of a private cloud, we're talking about the same kind of infrastructure, the same kind of services, the same kind of management and monitoring that cloud platforms come with, but inside your corporate data center, basically run by your own operations team. The actual contents of a cloud platform could be, with a little bit of simplification, summarized as a Servlet container plus plus. It's basically a pre-installed web container, web server arrangement with strong management and monitoring capabilities, inherent scalability capabilities. A very important characteristic of a cloud platform is its elasticity, its scaling up and down depending on demand. For the purposes of application development, for the purposes also of Spring, of course, most importantly, such a cloud platform comes with additional services, like access to the cloud platform's Datastore services, messaging services, cache services. How exactly those services are being obtained and what their life cycle is very dependent on the specific cloud provider. But from a Spring perspective, it really is just that, basically. A server-compliant web container accepting WAR files, standard JDK usually running underneath, and a couple of additional services that in some form you may have access to link them into your Spring-based application. Good examples, to put some names onto the plate here, are Google App Engine and Amazon Elastic Beanstalk, because both of them, even if they're actually quite different the closer you look, but both of them are basically a JDK installation plus a Servlet compliant deployment platform, plus additional services. There is some focus on JPA, but actually not too much, and a couple of specific APIs where you may talk to the native messaging services in those platforms, but it's not really more than that. Both platforms actually try to keep their standard infrastructure minimal. Anything else you would like to use within your application has to come with the application. So it really is the classic Spring model, and that's why Spring is such a great fit for those platforms. That's why Spring is actually showing up in quite a few sample applications that are typically being referred to for both Google App Engine and Amazon Elastic Beanstalk. There is no focus on providing a richer basic infrastructure platform such as Java EE. It really is about focusing on the essence of a server platform and leaving everything else up to applications. There are, of course, further offerings emerging. So Google App Engine and Amazon Elastic Beanstalk are actually two well-known ones that came quite early. There are further ones that we could dive into, but for the purposes of this presentation, I'd like to quickly dive into CloudFoundry, which is, of course, VMware's own cloud offering, an open source project, actually. So it's not quite like Google App Engine and Amazon Elastic Beanstalk in that it is not a hosted service with APIs for that hosted service. It actually is a standalone open source project, fully implementing those services and allowing to be installed onto by any kind of host, in particular also allowing to be installed in your own data center on your own machines. So it has a quite strong focus on this notion of a private cloud that you're running within your corporation. For the purposes of this presentation, actually, the most interesting part is up here, where we can see that the CloudFoundry platform overall is not actually Java-centric. It has a number of first-class application deployment models on top, application development models also that it supports. There is, of course, the Java world with a strong Spring focus in there, but there's also Ruby and Rails. There is Node.js. Many of those cloud platforms actually are not built on Java themselves. They are able to run Java. Java is a first-class citizen, but many of the services in those cloud platforms are implemented in other ways, native ways. The messaging services might not be implemented in Java and so forth. The data store services might not be implemented in Java either. So CloudFoundry is a good example for cloud platforms overall, in that it assembles a best-of-breed collection of middleware services that is very suitable to cloud-style elasticity. Java is a first-class citizen, but not actually Java-centric. In terms of terminology, we already talked about public clouds, hosted in the internet, basically private clouds running your own data center. We have this notion of a microcloud here, which is basically the full CloudFoundry infrastructure running on your development machine. So when you develop against CloudFoundry, you may actually develop against more or less the very same arrangement that you'll find in production as well. Again, the characteristic of cloud platforms that they usually provide such a developer installation. All right. From the perspective of a Spring-based application, it's just the same game. You're building a WAR file, you're selecting your versions of frameworks and libraries that you'd like to deploy into Web and Flip, and it all goes in a very abstract fashion through the deployment mechanism that CloudFoundry has into the cloud. So cloud-based deployment really is a very abstract perspective of deployment, as abstract as it gets. From an application dependency perspective or a development perspective, you really don't know much more than the basic platform specifications. You know it's a specific Java versions, you know possibly some limitations there, you know the Servlet version that it is compliant with, you know a selection of services that it comes with, and you really have to stick with those specifications. You don't control the backend service and the backend installation that is running there. That's the basic idea. In terms of the services, we'll actually get back to that in a minute. The services that come with cloud platforms are quite special, since they're not necessarily your traditional relational database plus XA transaction arrangement. Instead, you'll find a quite interesting selection of non-traditional data stores, NoSQL data stores, and also non-traditional messaging services that are not necessarily quite like JMS either. And CloudFoundry comes with quite a few pre-installed services, such as RabbitMQ, for example, for messaging. All of the cloud platforms, all of the three that we mentioned here, do come with a relational database option as well, at least in the meantime. Actually, the initial versions of cloud platforms tend to not come with a relational database option. It tends to be added later on. It's also quite interesting characteristic. So let's focus on the data stores for a minute, because this really has quite an impact on the application's architecture. We tend to see non-relational databases here, like the big table arrangement in the Google case, Redis, Mongo, Neo4j, key value stores, document databases, graph databases, very different kinds of data stores, really. Special kind of data stores optimized for special kind of data arrangements. Not all data is the same, and basically this choice of data stores allows you to pick the option, well, that's closest to your actual demand, that's closest to your requirements, where it's most natural to map your data structures onto. The idea of distributed caching, of caching in general, comes in very quickly as well, since some of those data stores are closer actually to a cache than to a traditional database, I guess. But fundamentally, caching is a key part of the application's architecture in any case, even more so with cloud platforms. Since in case of a cloud platform, you don't actually know how many instances of your application are running at runtime, where exactly they are running. They might be migrated at runtime to another node. So basically, if you'd like to interact with the cache, you really have to do it in a way that is appropriate for the specific platform that you're targeting. So cloud platforms tend to come with cache service options or to recommend specific cache service options. In terms of products, we have Gemfire and Coherence as typical examples for distributed caches that in their modern day incarnation are very suitable for cloud-style environments. An important characteristic, an important aspect is that standardization is not actually applicable to data stores, to non-traditional data stores, more or less by nature. Since many of those data stores have very specific ways of structuring the data, specific ways of querying the data, they need to have their own APIs. You can't just all treat them through the same kind of unified API. So if you'd like to develop against a specific data store of your choice, you're usually going to use a specific API, a specific Java binding, or maybe a part of the Spring Data project where we actually do support Spring-style Java bindings for many of those data stores, Redis, Mongo, and so forth, Neo4j as well. So you're going to interact with that data store of your choice. You're not going to pretend that you're talking to a general database of sorts. In terms of caching, there is actually a standardization effort, GSR 107. The number indicates that it's a quite old GSR, but it recently got picked up again for Java EE 7, for inclusion in Java EE 7. But only for caching, of course, not for any other data store needs. It's a pretty straightforward, reasonably complete specification for cache providers and for integrating cache providers into Java applications. Actually not too EE specific. The specification even has quite a strong focus on integration into Spring applications out of the box. So we're really talking about specific APIs coming up into this picture again. A typical characteristic of a Spring-based application is that we consider all of those APIs as first-class citizens. Basically, a JDBC-based database, data source, or a JPA entity manager factory are just as first-class as native integration with, well, native Hibernate, but also native Redis, native Mongo. We tend to consider all of them first-class. Spring Data, of course, is a sister project of Spring Frameworks because many of those data stores evolve very quickly. They evolve, in particular, more quickly than Spring Framework, the core itself. That's why they are in a separate project. But fundamentally, in terms of integrating them into a Spring-based application, in terms of managing their lifecycle as part of a Spring application context, they are all equally first-class. An interesting characteristic as a final note on data stores is that many of those data stores do not have traditional transactions either. They actually have their own, well, transaction-like mechanisms possibly, but no traditional transaction semantics in many cases. So that's also quite interesting characteristic here. The inherent scalability requirements of a cloud target platform really does not suggest traditional pessimistic transaction assumptions. They tend to be optimized for high concurrency and tend to make compromises in that area. It's not a topic for this presentation really, but an important and interesting characteristic of those recent data store developments. Another important topic here, maybe even more important in terms of the applications architectures, web clients, web application architectures. From a modern day perspective, we tend to not quite build web applications the way that we did it historically. The past 10 years, web applications were strongly about server-side state in particular, about managing server-side state. In recent years, recent developments, we are seeing a strong focus on HTML5 for a start, on rich HTML JavaScript-based clients, of course, also on other common rich client solutions such as Adobe Flex, even on native mobile clients like Android clients or iOS clients. All of them share the characteristic that a lot of the user interface handling, a lot of the user interface state, user interface navigation actually happens on the client side. The server basically turns into a, well, collection of service endpoints, often HTTP endpoints, RESTful HTTP endpoints in many cases, accepting JSON payloads, sending back JSON payloads, possibly also more specific payloads of your choice or of the UI technology's choice. The consequence from a server-side development perspective is that we tend to see less state, possibly even no state at all. In combination with authorization technologies such as OAuth, you might actually have no traditional session state at all, or at least strictly controlled, minimized user session state on the server, most of the state handled on the client. That has an implication, of course, on traditional web architecture assumptions. And GSF as a typical example for a strongly server-oriented web application architecture with strong focus on managing server-side state, traditional page state, might not be that great a fit anymore for next-generation web architectures. That's very generally speaking, since from a Spring perspective, we really support GSF as we always did, and GSF keeps evolving. There's GSF 2.2 coming up in 2012 here, and we will, of course, support GSF 2.2 as a first-class citizen in the Spring world. But fundamentally, we see a strong trend towards next-generation web architectures of the client-oriented kind, where server-side will actually developing HTTP endpoints using Spring MVC. Spring MVC is actually these days strongly positioned as an HTTP endpoint framework in many ways. And also JXRS, of course. JXRS is also strongly oriented towards that kind of application architecture and actually works just fine in integration with a Spring backend as well. So that's a strong influence onto modern day Spring as well. We tend to see a different kind of web architectures. This slide is actually really old. I chose to include it here since it really indicates that the focus of Spring always was about a combination of things here. This slide dates back to Spring 2.0, to the 2006 days, so it is like more than 5 years old. It indicates that on the one hand, Spring always was about dependency injection, and it still is, of course. It's a key capability of the Spring container. But it's not all that there is in Spring. Spring equally, well, was about aspect-oriented programming. Since Spring 2.0, our strong aspect-J support, it really has the richest AOP support on the planet, I suppose, among application frameworks. AOP tends to turn into more of a underneath the covers feature these days. If you're using Spring from a modern day configuration perspective, there's plenty of AOP involved, but most of it is underneath the covers behind declarative services that you're using in your application. Well, and down here, even back in 2006, we had a strong focus on portable service abstractions. Portable service abstractions such as the transaction management side of things, the task executors for running asynchronous task units. There are many services in Spring, many service SPIs that the Spring programming model refers to. We actually tend to have a pretty specific perspective when we talk about service abstractions. Service abstractions in the Spring sense don't necessarily mean that we are really literally abstracting a service so that you're not seeing it anymore, right? In many cases, we choose to integrate with the native services, exposing the native power of those services. In some cases, in quite a few cases, even the native APIs of those services. if you're using JPA in a Spring context, you're most of the time talking to native JPIs only, entity managers, entity manager factories. Modern day use of Hibernate in Spring means you're talking to Hibernate session factory, current session, the Hibernate session API. So we tend to integrate services into the Spring world in a fashion where we preserve their native power and still make them proper first-class citizens in terms of being integrated into the Spring lifecycle, being integrated into Spring container services, into Spring transaction management, into Spring resource management. So we really have a specific understanding of what we mean with portable service abstractions. And up here, actually also part of the original slide, we talk about blueprints, basically about guidance, about showing how things work in practice, showing how things work in integration with, well, everything that there is around. Spring doesn't live on an island. It is designed to live within a concrete system environment with a choice of deployment platforms, data store services, messaging services, choice of transaction management backends. Spring really is about trying to be a good citizen in any kind of system environment and trying to smoothly integrate both into newly established system environments and into existing system environments where, well, some things just have to be accepted the way that they are, and Spring is trying to make the best of what you got. This is really the positioning of Spring back then, and it still is very much the positioning of Spring today. All right, so let's move on to the selected features in Spring 3.1 part of the presentation, where I'd really like to present a selection of features. It's not a complete overview. It's not a what's new arrangement. Spring 3.1 comes with many improvements in the details compared to basically building on Spring 3.0 and just refining many things in the Spring 3.0 programming and configuration model. However, there are a number of themes in this release, and I'd like to present a selection of the major themes and some little bits that I personally find interesting, important, or just worth mentioning. All right, let's dive into it. A very important theme in Spring 3.1 is the environment abstraction and the features that come with it. Basically, we introduced a mechanism here for unified access to specific environment characteristics. And the goals, actually two goals, of this mechanism that we're working towards here are stated here. On the one hand, we would like to have a first-class mechanism for bean definitions to be activated in specific kinds of environments only. Basically, for the bean definition configuration to react to the specific environment that the application is being deployed to with a first-class mechanism. And beyond this bean definition model, we'd also like to have a more unified management of properties for resolution as placeholders. In the traditional Spring world, we always had property placeholder configurer, basically placeholders resolved against properties files, placeholders resolved against system properties. In Spring 3.1, we have a unified property resolution SPI now, a hierarchy of property sources where you may more or less centrally configure a hierarchy of property sources that all of your placeholder resolution is going to refer to by default. If you have a number of application contexts in your system, they can by default all refer to the same standard property resolution rules. And there, of course, you may refer to system properties, but you may also refer to WebXML context params, to JNDI environment variables, basically to environmental properties of your choice. This is highly configurable, and important characteristic is centrally configurable for a number of application contexts to all refer to the same resolution rules. So this is really, this is what we mean with environment abstraction, but it really is about those two specific goals. The bean definition profiles can actually be illustrated quite easily. It really is a very straightforward mechanism for associating specific bean definitions or a group of bean definitions with what we call a profile. Active profiles are being managed by the environment. So basically, at runtime, we can determine, at startup time specifically, we determine the number of, the set of active profiles. When we evaluate the bean definition configuration, we will only register basically the set of beans that is actually active in that profile. So in a traditional XML bean definition arrangement, you would use beans sections, in particular nested beans sections, and associate a group of beans within that beans section with a specific profile. If profile production is active, we will evaluate all bean definitions within this bean section. If profile embedded is active, we'll evaluate all bean definitions within this section. At runtime, there may, of course, be any number of profiles may be active. But in this case, it's quite obvious that those are designed as alternatives. So you would activate production or embedded. So one of those two data sources would become registered at runtime. Beans sections can actually be nested within the same file. So within an outer bean section in an XML file, you may have any number of nested bean sections, which means those alternatives, as shown on this slide, may actually live within the same XML bean definition file. Or they may also be factored out into separate files. But for immediate alternatives, such as shown here, you may actually choose to have them side by side in the same XML bean definition file within nested bean sections. Associating specific bean definitions with profiles may, of course, be done through the XML profile attribute as shown on the previous slide. But there's also an annotation-based equivalent. If you're using configuration classes, add configuration classes as introduced in Spring 3.0, you may associate configuration classes with specific profiles through the add profile annotation. This usually means that the configuration class groups a number of beans that are all meant to be activated in that profile only. You may, as an alternative, also choose to add the add profile annotation to specific component classes if you're doing component scanning. But in general, there's usually a trend towards grouping bean definitions into specific profiles. Of course, any bean definitions which do not have an associated profile, traditional bean definitions basically as you always had them in Spring, they are always going to be activated. So at runtime, we're basically combining the bean definitions that are always going to be activated with the ones that are only going to be activated in the profile that happens to be active at runtime. So it's a quite flexible mechanism that allows you to identify specific parts of your bean definition configuration that tend to change between environments. Those are the ones that you would group into a section associated with a specific profile. And of course, in the regular case, 80 or 90% of your configuration are going to remain the same across all environments, those you would have in traditional standard bean definitions without a profile associated. Activating profiles is actually a very flexible mechanism. You can do it through a system property, actually through any property in the property resolution chain in this hierarchy of property sources. But it may also happen in any other way. You may also use other characteristics where you check specific things at runtime and identify the active profiles that way. So it really is a very flexible mechanism. We tend to focus on ways to identify active profiles from outside of the deployment unit. Basically, you have your WAR file, your web application archive file. You do not intend to modify this WAR file. Basically, it remains the very same WAR file with the very same timestamp, but depending on where exactly you're deploying it to, that WAR file internally may react to this profile setting and adapt itself onto the specific target environment. This may be used for target environments as in deployment environments, so to differentiate between the configuration for specific servers, for specific cloud platforms. However, it may also be used for different deployment stages. You could also have a development profile, a testing profile, a production profile, and depending on which stage you're deploying the WAR file in, you would activate specific services. You would maybe fall back to simpler versions of specific services, fine-tuning the arrangement through the use of profiles that way. So let's move on to a related topic. Java-based application configuration is actually a kind of a next step after what Spring 3.0 did with the add configuration style. It really is about arrangement, the configuration class facility in Spring. And we'll see what this looks like stylistically in a second. The basic idea is that we would like to provide the same level of convenience that our XML namespaces tend to provide, but we would like to provide it for the add configuration model, for an annotation-oriented, Java-oriented configuration style. We're talking about things like TX annotation driven here, or the task namespace, about higher level container configuration features where you're instructing the container in some ways within your application. TX annotation driven is a good example where you activate a specific container feature in interaction with a specific transaction manager against a specific application context in your system. The stylistic choice here is intentionally not a one-to-one mapping from XML. We're trying to provide the same conveniences, the same kind of setup, but in a natural style, in a style that is natural within the add configuration model, within the annotation-oriented perspective. So it's not a one-to-one mapping. It also differs in naming from XML namespaces. And well, we already elaborated a bit on what kind of features you would find in this model. As a typical example, let's have a look at this add configuration class here. This is a Spring 3.0 style configuration class, really nothing unusual, except for this add enable transaction management annotation. We're providing a set of add enable annotations. Those basically map onto, or this specific one maps onto TX annotation driven quite naturally. This configuration class contains a number of supporting beans. So the transaction manager, the Hibernate session factory, and so forth, they would all be defined as add bean methods. What add enable transaction management adds here is that it instructs the container to basically activate add transactional processing, referring to this transaction manager by default. And that's basically it. When the container parses this configuration class, it does not just see the add bean methods, the bean definitions are coming in here through add bean methods. It also parses the add enable annotations and automatically activates the corresponding container features. Overall, this is it's an important piece of the puzzle in that it actually completes the add configuration model. If you choose to do so, you may compose your entire application configuration using component classes and configuration classes. Completely XML-free if you choose to do so, while preserving the same kind of configuration convenience that you are used to from XML namespaces, from Spring XML namespaces. As an important part of the overall picture, we also invested into an overhaul of the test context framework, of our integration testing framework, where all of the core Spring editions, the core Spring 3.0, 3.1 component model features are now first-class support now have first-class support in the integration test framework as well. In add context configuration here, you may refer to configuration classes, defining the configuration for that specific integration test. You may activate profiles for that specific integration test, where for the purposes of this test, you're basically activating a profile so that your configuration assumes that it runs within that profile. So some important features exposed to the integration testing framework as well, so that you can really not only compose a nice arrangement of application components and configuration, but also nicely test it in integration using Spring's test context framework. So before we move on to the next major theme, which is caching, I'd quickly like to take a minor feature in Spring 3.1. The C namespace, it's actually an XML namespace, so we are of course investing into the XML configuration story as well, and we identified an important gap in the XML configuration story, since we had a P namespace for inline property values before, but we did not have an equivalent facility for constructor arguments. So what we have in Spring 3.1 now is a mechanism that allows you to do this. Basically, inline CName constructor argument values, where you are passing specific values or specific references down here into a specific constructor argument. With the P namespace that we had since Spring 2.0, you would just say pname to invoke the setAge, the setName method, referring to bean properties. With the C namespace, we now provide a way to refer to constructor arguments by name inline within a one-line bean definition. The goal basically is to keep the XML bean definition as concise as possible, in many cases a one-liner. A specific twist here is that we are referring to constructor arguments by name. As you may be aware, in Java, constructor arguments don't actually have a name at runtime. They have a name in the source file, but when they are being compiled into standard Java bytecode, all that remains is basically an indexed types for constructor arguments and for method arguments. What we do here to overcome this limitation is that we are parsing debug symbols. So what you're seeing here only works at runtime when you're compiling your application classes, the ones that you refer to here, with debug symbols included, with the debug flag in the compiler. Then we're passing the debug symbols, which actually contain the source level names of those constructor arguments, and we match the configuration names here against those names in the class file. If you forgot to compile with debug symbols, you'll actually get an exception when you start up the application. It will complain that it is unable to resolve constructor argument names without debug symbols. That's a quite interesting minor feature, and it's also showing up in other areas. The deeper you dive with Spring 3.1, you'll find other areas where we're also using method names, constructor argument names, but primarily method argument names as an indicator, as a fallback. In Spring MVC, for example, at request param, if you don't specify a request param name, we're going to take the method argument name by default. It uses the same kind of debug symbol parsing mechanism. And there are other areas beyond that, but Spring MVC is an important one. All right, so much for this little C namespace. Let's move on to a major theme on our list, the cache abstraction. It actually is a strongly application-centric facility in Spring 3.1. What we're focusing on is cache interaction between application components and a cache provider. We're not trying to abstract the inner behavior of a cache. We're not really trying to predefine any behavior for the cache manager. All that we're doing is we're trying to provide a highly convenient, highly declarative way of interacting with a cache. And our cache abstraction supports that. There's actually an interesting historic side to this, that we always had an org.springframework.cache package, but up until Spring 3.0, this package just contained 2 cache factory beans in a subpackage. And now with Spring 3.1, finally, we're actually filling this package, this module, with a reasonably rich cache abstraction and declarative caching solution. The backends that we ship are rather straightforward. We do ship an cache adapter out of the box, and we will be shipping a JSR 107 adapter in Spring 3.2 once JSR 107, this standardized cache effort in Java E7, once it is actually final. We follow it quite closely, so the mapping is straightforward. The integration will be straightforward. JSR 107 is actually to some degree complementary to what we are doing here in Spring, because it focuses really on the provider side. It is a richer specification in many ways, in that it defines stronger characteristics for the actual cache providers, and does not focus as much on the cache interaction story, arguably. In any case, we will provide first-class JSR 107 support and try to do the best we can and go the extra mile so that JSR 107 becomes a natural part of Spring-based applications in the Spring 3.2 world as well. Cache managers are actually a typical thing to configure using profiles, because they might differ between environments. So here's also an obvious connection to the environment theme, the profile mechanism. In your target environment, you may have like an embedded caching service in your target platform, whereas in development, maybe you're using a simple cache arrangement. Typical example for what can be addressed through profiles, as shown before. In terms of cache interaction, we're focusing on a declarative caching story here. There is, of course, traditional programmatic access. Injecting a cache manager, add inject cache manager, and doing programmatic cache interaction is equally possible. But the interesting part here is the use of annotations, declaratively specifying cache demand using the add cacheable annotation. Here with load owner up here, it really is a role model. Basically, add cacheable says if cache annotation processing has been configured in the container, if it is active at runtime, the container will intercept this call, compute a cache key from the method signature based on this integer ID, will then, before actually invoking this method, it will check the cache whether there is an entry for this cache key. If there is, and if it's not expired, we will return it and not even invoke the target implementation of load owner. If no such cache value is being found, we will actually invoke the load owner and then store the returned owner object into the cache based on the cache key. This is highly configurable. Cache key generation is configurable. You may associate a cache region here that owners are being stored into. You may associate conditions under which this method is actually a candidate for caching, and all other invocations would just go straight through. You may evict specific objects from the cache. Whenever delete owner is being invoked, the framework would compute a cache key from this signature here, from the integer ID, and evict an object, the value from the associated cache region if there is any such value. So it really is about declarative caching demand expressed using annotations. It actually is intentionally named as cacheable because you may even deactivate it. You may even choose to deactivate caching completely, and your application supposedly keeps working. Caching has just been deactivated. That's why it's cacheable. It supports caching. It does not necessarily rely on caching. So this is a quite sophisticated model, and I can only really show the basic design here, the basic style. Check out the Spring reference documentation and the examples that we're providing to find out more. All right, on to the last one of the major themes. We have a quite strong Servlet 3.0 focus in this generation of Spring. And with Servlet 3.0, we're really focusing on a specific enabling feature. In Servlet 3.0, there is a new mechanism for bootstrapping web applications. It's called Servlet Container Initializer. This mechanism down here is a key Servlet 3.0 feature. It basically allows you to define programmatic classes that the Servlet container finds at runtime and invokes with no WebXML involved. For the first time ever, we can compose standard Servlet web applications without WebXML. We're integrating this into Spring in a specific fashion with a mechanism called WebApplicationInitializer. I'll give you an example on the next slide. In combination with other Spring 3.1 features, such as the annotation config, application context story, the environment abstraction, this really provides a very rich model for bootstrapping Java-based web applications using standard Servlet 3.0 facilities in combination with Spring facilities for a completely XML-free web application setup, if you choose to want it completely XML-free in the first place, of course. There is more to Servlet 3.0, but for the purposes of this presentation, I'll just quickly mention it for completeness. We support Servlet 3.0-based multipod resolution, but further Servlet 3.0 support is coming in Spring 3.2, asynchronous request processing as the most important one, in case you're wondering. For the purposes of this presentation, let's focus on the Spring 3.1 web application initializer mechanism. This really is very straightforward, as indicated here. Basically, at runtime, their Servlet 3.0 container is going to find Spring's Servlet Container Initializer, which in turn finds all web application initializer classes in your deployment unit, in your WAR file. And Spring will then invoke those web application initializers at a very early stage of processing in order to compose your web application configuration. Basically, here within onStartup, you get a Servlet 3.0 Servlet context, which has methods such as addListener, and you're composing your web application configuration, your listeners, your filters, your servlets in a programmatic fashion. This really is a very rich model. So you can build a Spring application context as an object. You can instruct it programmatically and then pass it into a context loader listener as an object reference. It is all instance-based instead of the WebXML, class name, context param, string, property base. So this really is a rich object-oriented configuration model for Servlet 3.0 web applications. If you're registering a Spring Dispatcher servlet, it works just like that. Build an application context object for this Dispatcher servlet, and then say basically servlet context add servlet new Dispatcher servlet, pass in the application context as a constructor argument. It really is a richness to servlet-based configuration that just hasn't been there before. And that's why we really love this feature in Spring 3.1, in interaction with the Servlet 3.0 facilities underneath, of course. If you're running on a Servlet 3.0 container, definitely check out the options here. All right, for completeness, it's not the focus of this presentation. There are also plenty of Spring MVC enhancements in Spring 3.1. We have a completely new, very flexible, very composable backend for processing annotated MVC controllers. And if you're into customizing Spring MVC, this is definitely of interest to you. And as just one of the new features we added in Spring 3.1 to Spring MVC, we have first-class Flash support now, richer, more fine-grained control over how a redirect is being processed, in particular how redirect state is supposed to be handled. Traditional Flash attribute handling basically in a typical Spring-style way integrated into Spring MVC. All right, and to wrap up this presentation, I'd just like to show you a couple of little things related to integration with third parties. Well, JPA is not exactly a third party, but we did focus on the JPA support for a specific reason. In standard JPA, you have to have persistence XML. Basically, JPA identifies a persistence unit through the persistence XML file. In Spring 3.1, we provide a mechanism to build a default JPA persistence unit from a selection of packages that you specify. So no persistence XML involved, rather Spring-style package scanning, component scanning, where you just specify the root of your application packages, and we search for all entity classes and compose them into a default persistence unit. This is similar to a feature that we had for Hibernate before, so it shouldn't come as a surprise, but we provide it for JPA now. And in combination with the Servlet 3.0 bootstrapping features, where you can avoid WebXML and the new Java-based application configuration features, where you don't need to use Spring XML namespaces anymore, you can literally define a complete Java web application, including the use of JPA, with no XML involved, no hidden XML either, in comparison to other solutions out there in the market. And as a minor feature, we have consistent support for JPA setup by persistent unit names for more complex arrangements where you have several persistent units in the same application. We have consistent support for relating to persistence units by name now, even in all Spring components like JPA Transaction Manager. All right, and in terms of actual third-party updates, we support Hibernate 4.0 now through JPA, but also natively. Due to changes in the Hibernate APIs, this lives in org.springframework.orm.hibernate4. It's a separate support package for Hibernate 4. Our Hibernate 3 support, of course, is still included in proper form in the orm.hibernate3 package, just like before. We also support Quartz 2.0 now. Again, plenty of changes in the Quartz APIs there. We do that within the same package, so org.springframework.scheduling.quartz. You'll find a couple of Quartz 2.0 characteristics in there. If you're into Quartz 2.0, check out the Java doc. In particular, check out the new factory beans for job details, ground triggers, and simple triggers, which are Quartz 2.0 compliant. Last but not least, we also have Java 7 support. So Spring 3.1 auto-detects Java 7 at runtime. If you're running against JDBC 4.1, we'll detect it and automatically use it in parts of our JDBC support. And we have some support for the new fork join framework in Java Util concurrent as well. So in the meantime, we have not only OpenJDK 7, we have Oracle's JDK 7 distribution, and we have IBM's JDK 7. So we expect Java 7 to become common quite soon. Spring itself is not actually built against Java 7 yet, but as of Spring 3.2, we'll build the framework itself against Java 7 as well. We, of course, keep compatibility with Java 5 and 6. So we keep compiling with source 1.5 and target 1.5, but in order to make full use of Java 7, as of Spring 3.2, the framework itself will build against Java 7, as a side note. All right, so much for this tour through Spring 3.1 features and the context that Spring 3.1 lives in. We really position Spring as an enabler for modern enterprise Java architectures these days. So there's a strong focus on not only a complete programming and configuration model, but also a strong focus on deployment platforms, on taking the current crop of deployment platforms, including cloud platforms out there, and providing first-class support, providing mechanisms that are an ideal fit for the next generation of deployment platforms out there. Java 7 and Server 3.0 are important common ground. We expect those to be the common ground for quite a while from now on, where the mainstream typical Spring-based application will be developed against. And in Spring 3.1, we of course have a selection of features targeted for this modern world of modern deployment. The environment abstraction, we talked about bean definition profiles, our declarative caching solution, the Server 3.0 support with web application architectures, web application deployment that do not have to use WebXML anymore. And we have a strong focus on being compatible with the latest platforms as well, Java 7, Server 3.0, but also third parties such as Hibernate 4, Quartz 2.0, and many of the third-party data stores in the Spring Data project, where we support the latest versions of Redis, Mongo, Neo4j, and so forth. So much for this tour. If there are any further questions, please use the usual feedback channels. We blogged about many Spring 3.1 features. Feel free to comment on those. If you have specific improvement requests or the like, please go to our issue tracker and you'll possibly even find an existing issue there, which you're free to comment on. Other than that, well, hope you enjoyed the content in here and it actually helps you in making your choices on the way forward. Thank you for listening and have fun with Spring 3.1.